Hola.
Hola, profe.
Hola, hola.
Any questions before we start? No? Okay, let's see. So we've got a lot to cover today. So we talked about Bremsstrahlung, braking radiation, and so in particular we had set up a Coulomb field for interaction between an ion and an electron, right? And then we did the sort of dipole approximation. We did the cylindrical sort of assessment of different impact parameters. We ended up deriving a amount of work per frequency, per volume, per time. And we got something that looked similar to past estimates with a logarithmic dependence or natural log dependence on the impact parameter, a dependence on the densities, dependence on the atomic number, essentially the charge, and the velocity, right, plus some constants. So we had evaluated what these B's could be, and we actually end up putting this in as we call a Gaun factor. And I'll show you a plot of a Gaun factors in a few slides. But it encapsulates all of this. So the next thing to do, this was for a single electron and a group of protons. And so the next thing to do is actually integrate over some distribution of electrons. And so the simplest version of this is a thermal distribution, right? And so this is what's known as thermal Bremsstrahlung. And so this is a very common situation where you have, for instance, an ionized region, which is come into equilibrium. And so you have a central ionizing source, a star, and you have a H2 region, or you have a hydrogen gas bubble, right? And you ionize it. And so at some point it will be in equilibrium and it will deliver something like this. So we had a single speed expression before, and we can replace that with a thermal distribution of speeds. And so to do this, we can express some probability of a particle having a velocity within some range in velocity space. And so this probability is going to be proportional to, this derivative of the velocity range, and then this thing here, which is just expressing, a Boltzmann distribution. And so this thing, if we take this energy equal to the energy of our electrons, it will have this sort of form, 1/2 mv squared, so it'll look like this. And this volume we can break into a sort of surface area and then a thin shell, right, or surface velocity distribution and a thin shell. So this is what we would see for an isotropic distribution of things moving in and out. And so this probability distribution, if we just fold these in, will look something like this. And so then we can integrate over this function. And so naively, we would start by just integrating from 0 to infinity. However, we have to note that actually there will be some cutoff velocity above which we don't need to really care anymore, because this is a thermal distribution. And so we can also note that the frequency is related to the incident velocity through something like this. And so basically a distribution with this average velocity isn't going to create a photon with this average energy. And so this is what we call the velocity cutoff, is due to photon discreteness effect. And so what this really means is that because we have a limit in velocity, we'll have a limit in frequency. And so in practice, this is what it looks like. So we have, say, this is our probability distribution as a function of frequency now, and we can express the velocity distribution as a temperature. So the average velocity of a particle, so 1/2 mv squared is equal to kT. And so we can express this distribution of velocities as a temperature. And so for a temperature T equals 1, typically we'll have a probability distribution which is flat at lower temperatures or lower velocities, and then cuts off right at the velocity of the average velocity of the system. And likewise, if we had a similar system with a higher temperature, it would look like this. And so, you have, for higher temperature, you have a larger number of velocity bins, and you have to have the probability distribution normalized over those. And so this is why this is lower than this, right? So if these are normalized, you typically have this exponential cutoff. In terms of we can think of this in terms of the acceleration as well. And so we have a perpendicular and a parallel sort of acceleration trend. And so if we divide these into the components I1 and I2, the perpendicular component has this sort of form, and the parallel component has this form. And so it's much more diminished than the perpendicular component. You would add up both of them to get the whole thing. So this is sort of an ideal case. This is what you end up seeing in practice, say in the X-rays. And so this is a very hot source with something like, we don't see the peak at all, but we basically see this exponential cutoff here. And these are in weird units, of course. So we can characterize this distribution, and basically what we want to do is integrate the power that comes out per unit volume, per unit time, per unit frequency. We want to integrate this over all possible velocities, right? And so we can do this in the following way. So we take this probability distribution and we multiply it by the individual amount here, right? And then we want to sum over all those states, or integrate over all of that. And of course, we normalize it by this factor here. So this we do from this minimum velocity here to infinity. And again, this minimum velocity ends up being equal to this thing. And for the frequency, we can shift and do something like this. And so in doing these integrals, we end up with something which ends up looking rather decent. And so we have this Gantt factor here is now the average Gantt factor. So we've kind of averaged it over frequency and whatnot. We're not over frequency, we've averaged it over the particle, the velocities of the particles.
Professor,
yes.
I have a question about the infinity value of the integral. We have the limit of the velocity of light.
Yeah.
So
this is
I didn't understand.
Between Vmin and infinity, this is between 0 and infinity, is what you're asking.
Yeah.
right? Yeah. Right. So basically, we could take this from 0 to infinity, but the issue is that this can be approximated by this integral, which I think maybe didn't necessarily explain very well here, but yeah, basically, so this thing, we basically would say, okay, initially we do this, but we have the fact that generally we are going to have this relation apply. And so we have to have this velocity here has to be at least larger than this photon energy, the equivalent photon energy. So if it has an energy equivalent to 1/2 mv squared, so plug in whatever velocity you want here, 100 kilometers a second. Generally speaking, that this relationship has to hold. And generally, this particular electron could not create a photon with an energy greater than this, right? Because it would have to get it from somewhere, and it doesn't have that energy. And so, in essence, you have a limit here on the photon, so it's a photon upper limit, and so this ends up being sort of equivalent to a minimum velocity in this sense.
Okay, thank you.
I mean, it's just a simplification more than anything else. We could do the integral, but we don't need to. Okay, so in doing this integral, we plug in this thing here, and so the only really nasty business is this thing, which we just average over, and then we just have a 1/v here and some constants. And so when we plug in 1/v here, we get v. And that's not so bad. So v times exponential to v squared dv. That's our integral. We can do that, and so we end up with, we retain this integral, we re-plug in here, rather than this velocity, we end up plugging in its sort of equivalent frequency, or its equivalent energy. And so we have this is the amount of energy that comes out of the amount of work that is done as a function of frequency now, as a function of this volume and this time. And so we can equate this thing with an emissivity. And this is the emissivity of free emission, ground control emission. And so if we evaluate all of these constants, we get this factor here, more or less. And now we have something where we can, for a given density and a given temperature and a given frequency, for a given density, for a given temperature, for a given atomic number, for a given Gaunt factor, and for a given temperature, we can calculate the emissivity as a function of frequency. That's basically what it comes down to. So this factor here comes from this thing here. So when we've turned all of the velocities here into temperatures and into frequencies to sort of simplify it and say, okay, this is a function of the temperature of the system. If the system is in equilibrium. And again, this factor comes from this velocity cutoff due to this discreteness function. Regarding this Gaunt factor, we can show it here. And so this is our average Gaunt factor for free frame emission as a function of, this is a normalized temperature. So this is frequency versus divided by temperature. And these are for a range of temperatures or velocities, if you will. And so why they choose these particular units, I don't know. I think Rick and Lightman just pulled the plot from somewhere else, but you can see that there's not a huge difference. So this is 5 orders of magnitude in, well, this is gamma squared. So this is 5 orders of magnitude in temperature. And there's really a very marginal difference in the Gaunt factor. This isn't log, this is the actual Gaunt factor. Right? So we're talking about this thing changing by a factor of a few over many, many orders of magnitude. And so this is also frequency versus temperature. Again, huge orders of magnitude. So in general, you can kind of get away with just choosing a Gaunt factor of something like 1 or 3, and you're going to be fine. So you can always do a pretty good estimate without actually digging into the functionality of the Gaunt factor. That's the major point. Here's another version of this. Now plotting it just as a function of wavelength. This is the Gaunt factor as a function of frequency and temperature. And so you can see it's pretty much 1 for very high energies, very short wavelengths. And then it sort of scales, excuse me, as you go into the optical wavelengths. But this is, for, again, a factor of 5 in temperature here. So it doesn't change too much. This is the actual functional form. So you can see that this overall flux changes by a huge amount over this wavelength range. And the mass, this is essentially it's the absorption coefficient, but it's the mass coefficient divided by the density squared also changes by a huge amount. And so you can see that this is a very slow moving factor because it's in the natural log. We can also show this plot, which is sort of an analytical formula for evaluating the Gaunt factor. So a little bit different terminology here. They use G here. And so depending on what this ratio is and what this ratio is, and this is in units of Rydbergs, you can use a small, this sort of approximation for what it should be. And so you can kind of plug it in and get a decent functional form in certain regimes. Okay, so that's emissivity. And you have some amount of electrons interacting with some amount of protons, you will get some emission that comes out as a function of frequency. What is sort of interesting is that with every emission process, there's an absorption process. And so while these electrons are emitted, they also have the potential to absorb. And so we can relate the absorption of radiation via an electron moving in a field of this ion based on the emission process. And so if you recall back from lecture 2 or 3 in chapter 1, we had this particular equality. And so this is the average emissivity, the isotropic emissivity. That is going to be equal to the absorption coefficient and the Planck black body. So if everything is in equilibrium, we will have some absorptions which match some emissions, and they're related by this thing. And so again, we can relate this. The emissivity is this J value is just the integral over 4 pi of our emissivity, right? And so we have our emissivity here, and so we can just plug that in, and this allows us to derive an absorption coefficient, which looks very similar, obviously, because it's just related, but we have this extra factor here, which is related to the Planck function. And so you'll see, this 1 minus e to the h nu divided by kt. That comes from the Planck function. And we also have an extra factor of frequency now. Actually, several factors of frequency. So what this looks like is that this absorption is a very strong function of frequency, right? Up to a certain point. And at that certain point, then it stops really being an important sort of component, which is what comes in here. So once this gets very, very large, right, this will then go to zero, or absorption goes to zero. And so at very, very low frequencies, this will be very, very high. So at very long wavelengths in the radio, you will have absorption. So most of the photons might actually be absorbed. And you only see photons which come out at higher energies, higher frequencies, shorter wavelengths. Calculating this, we end up with something which looks like that as a function of frequency. So if h nu is much, much greater than kt, then the exponential, this becomes negative. So we just get that this is proportional. Oh, there's a proportional sign missing here. Okay, there it is. I just realized I'm not in presentation, so it can be bigger. Sorry for squinting. Okay, so this thing is proportional to the third for h nu much less than kt. Basically, when we have, let's see, is this right? So, yeah, we basically have a Rayleigh Jeans. When this is the case, we're in the Rayleigh Jeans regime. When this is the case, we're here. So this thing in the Rayleigh Jeans limit becomes this. So we can sort of have we can approximate this by a Taylor expansion and then move this out. And so we end up with a slightly softer function of nu. So it goes as nu to the -2. And you'll notice that nu to the -2 is the same slope that we had for a black body, right? Now there is a mild dependence here on frequency. So it isn't perfectly nu to the -2, but it's decently close. And so we can, again, if we evaluate this, we can end up with something that looks like this. And so if we, this is a version of this where we do a, in Rick and Laitman, they estimate this as the Rosslyn mean. So if we take a slightly different absorption coefficient for sort of diffusion, then it would look like this. And so it has a much stronger factor. Well, basically you've moved this nu squared into the temperature. And so this has a very strong temperature dependence here, but no frequency dependence. And that's the only major change here. Just to give you an idea of the differences. So with that in mind, we can kind of ask what this might look like. And so if we have some initial spectrum, so basically what happens is at very high frequencies, you will have more or less a constant emission. And then once you get to about a tau of 1, where the absorption coefficient becomes strong, you get a turnover and you have something which rises as nu to the square. And so this is the overall emission that comes out of something which is emitting in thermal Bremsstrahlung. So you have an optically thick portion and an optically thin portion, right? And so another way of visualizing this is the following. So let's say we have a region that is of a fixed radius of 10 to the 15 centimeters. So that's 0.1% of a parsec, more or less. So So it's a relatively small sort of region, but something on the, I guess, on the orbit size of Saturn or Pluto. And then you have something which is, say it's a sort of constant, and it has a temperature of 10 to the 7. And we can vary the density, the average density in this sphere between 10 to the 10 and 10 to the 18. And that's what's shown here in these different curves. And so at 10 to the 10, you have, you don't have that much emission because the emission goes as the square of the density, or the, NE times NP. So the emission is down quite a bit. What that also means is that tau is proportional to the number density, right? And so you have much lower optical depth because you have fewer particles. And so the turnover happens at lower frequencies. And so then you have the optically thick portion, the optically thin portion, and this is flat up until you get to the average velocity of the system, and then you have a cutoff, an exponential cutoff. And so this is the Bremsstrahlung spectrum for 10 to the 10. If you increase it 10 to the 11, you will increase the overall intensity by n squared, right? So a factor of 10 here is a factor of 100 here, and so on and so on and so on. Likewise, you will increase tau by the number density, so you'll increase it by a factor of 10 each time, right? And eventually, you get to the point where it's so dense that the optically thick portion starts to run up against the exponential. And lo and behold, you end up having something which is akin to a black body, which is interesting. We didn't derive that at all, right? But this is in part because we enforced this condition, so for them to be in equilibrium. Okay, so that's just to give you a perspective of how these things change with parameter space. We can do a similar thing where we now have a fixed radius and a fixed density, and it changed the temperature. And so here is for t to the 5, t to the 6, t to the 7 for this relatively low density. And so what you can see is that for lower temperatures, you have obviously you have a lower cutoff, right, by a factor of 10 each time. But you also have that the optically thick portion of this increases as well. Why is that? That's because this absorption goes as the inverse of the temperature, right? So a lower temperature means more absorption and a higher cutoff. And so we get a cutoff here. So most of the energy comes out over a shorter range of wavelengths for lower temperature radiation. And ultimately, if we decrease this temperature by another couple of factors, we will end up with a black body again. And so at some point, you can no longer generate, Bremsstrahlung from a relatively low temperature gas, which also physically, once you have a low temperature, you will have the atoms, the protons, and the electrons bound. So again, it physically makes sense. Okay. Any questions on this? This is all sort of classical Bremsstrahlung, and we're now going to move into the regime of relativistic Bremsstrahlung and see how this differs. Everyone's happy so far? As much as you can be, okay. Right. So let's now think about what modifications we have to have in order for us to take into account relativistic Bremsstrahlung. So where in our formula, do we have to, what modifications do we have to do in order to deal with high speeds? And here we're going to use a method called the virtual quanta. And this will then harken back to, what we were doing with sort of photons versus true particles. So we're going to consider a physical situation where we have an electron and a heavy ion, just as before. The ions move relatively slowly, and so the electron does most of the movement as usual. This is all in the rest frame of the medium. So we have a sort of situation which looks like this. We have an ion, it has a Coulomb field, which looks like this. It has a velocity, and we have the electron here. So we've inverted the frames, right? So we're going to shift to a frame where the electron is at rest. And so our electron is at rest, we have an impact pattern of the electron, and the ion is now moving. Right? And so we now are in the situation of the ionization losses, more or less. So we have this electrostatic field of the ion. It's going to transform into a traverse pulse where the E and D fields are sort of equal but perpendicular to each other. And this is going to appear as an electromagnetic pulse as this thing gets faster and faster, right? So this shape will become a delta function as the speed approaches the speed of light. And so the radiation is going to then Compton scatter off of this electron to produce emitted radiation. So we're going to look at this thing as if it were a photon, and we're going to apply a Compton scattering of this in order to see what happens to the radiation. So if we transform back to the ion frame here, we then should have the classical case of Bremsstrahlung. And so all that we're really doing here, the relativistic form of Bremsstrahlung is effectively a quantum scattering of a virtual quanta of the ion Z field as seen in the electron frame. That's the transformation we're effectively doing. And so in mathematical terms, we have in the primed frame here, we have the spectrum of a virtual pulse will be given by this thing, which you recall we calculated before. So this is our friend, I'm blanking on the name, the modified Bessel function. So modified Bessel function squared of the first order, right? And so we also have our impact parameter, our frequency, and our gamma. And we've set here the velocity in these equal to the ultra relativistic limit, because this is going to be a virtual quantum for the moment. And so we then want to examine the system as in the primed frame. What's going to happen is that we're going to consider that the electron is scattering according to the Thomson cross section, and so it should behave something like this. If we had to deal with a more quantum mechanical limit and ultra relativistic case, we might end up using the Klein-Nishini cross section, which would be applicable for energies which are less than the rest mass of the electron. So basically this, this will occur, so for frequencies which are lower than this, we have a sort of low frequency limit here. For frequencies that are higher than this, we can sort of treat it as this. So in a low frequency limit, is that correct? I think I have this mixed up for some reason. I always get only slightly confused here. Let's see. I feel like I have it incorrect. So this is for frequencies. This should be, I think I have these mixed up. That's why I have, that's what, okay. I changed the font and I think I screwed them up. Sorry about that. Okay, that is much less confusing now. Okay, so right, so in the low frequency limit, we should have the Thompson scattering, and in the high frequency limit, we'll end up having to invoke the Klein-Nishini. So for the low frequency limit, we end up with something which looks like this. So we have the energy per frequency per area times the cross section will give us the energy per frequency. Okay, so this thing and this thing should transform uniformly under a Lorentz transformation. Because remember, there's one gamma here and there's one gamma here, and they divide out. And so these are invariant. And so what we want to do then is write this thing in terms of B and omega rather than B prime and omega prime. So if we plug all this in, we want to rewrite these things in terms of B and omega. And so B should transform because this is a traverse length, so it should remain unchanged. Omega, however, will change as delta omega prime or gamma times this angle here. And this angle is the scattering angle for the scatter in the electron restaurant. Okay, so plugging those two things in, we can also notice that this particular thing has front-back symmetry, and so if we average over that, we'll end up with something like this. And so the emission in the ion frame now should look like this. And so we have an extra factor of gamma here in this conversion. So we can then think about this in terms of the pure time and per unit volume. So if we want to calculate this energy per unit frequency for the collision of an ion and a relativistic electron at some impact parameter B, we have our densities here. We basically can repeat all of the other arguments that we did before, but instead we replace V with C. And that's the main difference. And then the minimum that we use here, we would use H divided by MC for the uncertainty principle. And so the only difference between the past formula is an extra factor of gamma and C. And so in the low frequency limit here, so this thing here, remember we've now converted this from omega prime to omega, so we have an extra factor of gamma. This thing should roughly be proportional to this. And so we end up having 4 factors of C here instead of the sort of V as we had before. At high frequencies, we would plug in the Klein-Nishini correction. And so this Klein-Nishini correction, if we plug all these in, we have this extra relativistic correction here. So this thing is our Gantt factor again, but we have this extra sort of velocity correction, which we can put in terms of temperature if this thing is in a thermal relativistic plasma. Okay. So what's sort of interesting to look at is the cross-section as a function of angle, of scattering angle. So remember, for these formulas, we had averaged over this. But if we want to actually look at how this will come out as a function of solid angle, you need to consider the solid angle, well, the cross-section is a function of solid angle. And so here, we would have the differential cross-section, which we have calculated before. So it looks something like that, where this is the classical electron radius. And so if we integrate this, we end up with the Thomson cross-section, right, in the low energy regime. Now, if we want to consider dealing with sort of high energy photoelectric and Compton scattering effects, this is what Klein and Nishini derived. And so they derived a solid angle which looks like this, much uglier form. You still have our electron radius squared here, but you have this function which comes in several places and at various orders, in addition to this theta dependence, the sine squared theta dependence. So this thing is like this, and this factor here is our ratio of the frequency to the rest energy of the electron. And so obviously, if this is very, very low, this is 0, and this thing is just 1. And so this thing is 1, this thing is 1, this thing is 1. And so you end up with 1 minus cosine squared, which you, I think, can convert back to getting the regular cross-section. So this extra factor, though, is, deals with the beaming effect. And so these are polar plots showing as a function, this is the cross-section as a function of solid angle, and it shows a particular scattering angle, and then the total cross-section. And this is for a kinetic energy of 0, so very, very low, and you have just the classical Thomson cross-section, right? So front-back scattering symmetry is shown by this solid line here, and this is the relative, sort of scattering for this angle. Or rather, this is the value for this particular angle. Now, if you increase the speed to 0.01 MeV, so still pretty small compared to the rest energy of the electron, which is 0.5, you end up getting some interesting effects, right? So the scattering here is now dominated by the forward component, right? This is the relativistic beaming that we had discussed before. The cross-section is now different. The overall integrated cross-section is now slightly different, but not too different from this. The actual cross-section in this particular direction, which is this one here, is slightly less now. So we have more forward scattering. So this is less than this. And then we have an extreme case where the energies are almost ultra relativistic. And there you can see immense forward scattering. And also the blue is the recoil from this electron, right? So you end up having a strong recoil, which is shown in blue here. So this is the classical case, and then, this is the classical case, and so this is then this new cross section. So you can see it drops quite a bit in this particular direction, because most of the cross section now goes in this forward direction. Okay, so that's just to give you an idea of how this works. Okay, at very, very high energies, so above 100 MeV, pair production becomes a dominant sort of effect, and ends up strongly clipping this process. All right, so that's this sort of relativistic version. If we have that, there's not a huge amount of situations where you would have thermal relativistic electrons. You would need very, very hot plasmas, so 10 to the 8 Kelvin or so. Yeah, that's about 10 keV, and so you do have those physically in some places, but they're relatively rare. And so in that case, you would need to account for the relativistic corrections. Okay, questions?
I have a question for the, I don't remember the name of the G parameter in the equation, the previous equation.
This
This
one?
one, yes. Right, so I noticed the coefficient B changes from the previous equation, so.
This is just B for Bremsstrahlung.
Okay, no difference.
I mean, no, only that, yeah, you, depending on if they call it free or Bremsstrahlung, they're fairly equivalent. But yeah, Bremsstrahlung is more common in some circles, free in others. Typically at high energies, we talk about it in terms of Bremsstrahlung, and then in low energies, we typically talk about it as free emission.
Okay.
But it's mostly historical, I think. But yeah.
Okay.
This is still the count factor. It just has this relativistic correction. So I think what they've done here is moved out the normal version of it, which is coming from back here or here, and then you're now in a regime where you have very high energies and sort of in very short wavelengths.
Right. Okay.
Yeah.
Thank you.
I mean, you end up seeing this Gaunt factor is a very common, because this thing ends up being very common. This B min over B max cylindrical sort of interaction mathematics or scenario, how you integrate things. The Gaunt factor tends to be pretty ubiquitous. And so there will be Gaunt factors for lots of different types of interaction. So it'll be a Gaunt factor for free, or it'll be a Gaunt factor for something else, inverse Compton. So you'll see it a fair amount.
Okay.
And generally, you can either just look up tables or get a functional form and try and calculate it. Yeah, and again, we've only been dealing with thermal Bremsstrahlung, but you could imagine cases where you don't have a distribution which is purely thermal, in which case then it becomes trickier to calculate, much trickier to calculate. So, yeah. Luckily, many situations end up becoming thermal on relatively short timescales, and so you can kind of get away with this in most cases. Okay, so let's now look at the applications. So I have a lot of applications to round out the lecture here. So, if we want to actually see this, we need to have a region which has a significant fraction of ionized particles and free electrons in order to generate the radiation. And this occurs in a few places. The stellar corona, right, is one place where we have ionized regions. And so magnetic heating and then collisional ionization will generate these particles, which can then generate Bremsstrahlung. And so when we look at the sun in X-rays, we see that the halo, the corona glows, and it goes because of Bremsstrahlung radiation. Another place we can see this is in photoionization regions around very strong UV emitting sources, either hot stars, young stars, massive stars, or white dwarfs, where they have a strong number of photons with sufficient energy to ionize hydrogen. These create H2 regions, and actually AGN are another place where you see this. And so you have stars, AGN, and planetary nebulae will generate this. You can also do this from, if you have ionized winds or jets, you can also do this sometimes. Then another place you can see them is if you have collisional ionization. So if you have very deep potential wells, such that the average particle temperature ends up being above 13 EV, then you will end up ionizing a portion of that medium, and then it will cool via Bremsstrahlung. So galaxy clusters fall into this category. And then you have collisional ionization from shocks. And so supernovae and supernova remnants fall in this. And we'll take a closer look at each of these things. So if we have, yeah.
I have a little question. So the previous plots, when you showed like the pattern of the radiation is the Westralian pattern that could be that it's would see the in the ions frame and yes, in the ions frame. And when we are placing in the electrons frame, we normally expect to see the Bessel function, but in this case would be the angular dependence of this Bessel function of the emission of the since in the electron frames.
Right. So I mean, the benefit of thermal plasmas that are relativistic is that they average over all angles. And so you will end up getting a boosting, which happens in every, in all directions, but the overall emission ends up the conservation of energy applies. So you might change the spectral form a little bit. Typically, you boost out the this cutoff. You'll move it out a little bit due to this boosting, but you will also bring it down a little bit. And so if you integrate over the entire thing, because you've averaged, because there's a thermal equilibrium, you still can end up deriving relatively consistent parameters and properties of the system, but you do have to take into account the modifications in spectral shape. Does that make sense?
Yes, but my question is more regarding the geometrical, especially in the space, the pattern of emission. I don't know if in the case of in the frame of the electrons, the radiation should be like spherical, or if there is a.
Well, I mean, you have to differentiate between individual interactions and integrating over large numbers of interactions. Right. And so when you integrate over large numbers and over a velocity distribution, then you end up averaging out most of the angular dependence. So the shapes don't really change too much, but the energy that the photons come out at will change a little bit, because clearly if you have, you have, rather than this process generating photons which can go in all directions or most directions, what you end up doing is beaming them, right? So you give them a Doppler boost in frequency in a certain direction, and you never broadcast anything in the other directions. And so what it'll end up doing is stretching out this spectrum that we have, right? So it'll end up stretching it out and flattening it, because if you integrate over the entire thing, you still have to have a conservation of energy effectively, because the system is doing this in all directions. Now, you could also imagine situations which are not symmetric. You may have things which have different velocity profiles in one direction versus another, and then you will have some dimensionality to it. Yeah, it just complicates things.
Okay, thank you.
Okay, but yeah, in terms of the relativistic correction here, I mean, you can look at how this thing compares. These factors are all the same. This is a little bit different, and you have this extra term here, but it's a very small correction. So you need temperatures of the order of 10 to the 10 or 10 to the 9 in order to start seeing any sort of correction here on this. And so that's quite high. So it's rare that you end up seeing two really strong corrections from this Klein machining factor. Just to compare it, let's see, so we go back to so this was as a function of frequency. And this, I think this was, yeah, so this is missing per frequency. So this is also, it ends up being relatively flat, and it's not really a strong function of frequency above a certain limit. And so it's slightly difficult to compare it directly, but yeah. Okay, so mostly in the case of not dealing with ultra relativistic bremsstrahlung, we can give you all of these possible examples. So the easiest one, I think, is to start with is bremsstrahlung from H2 regions. And so you imagine you have a collection of neutral atoms of hydrogen with some number density and 0. And imagine that they collapse down and they end up forming a star. The star turns on. All of a sudden, the star has a lot of UV photons because it's very, very hot. And so it's approximately a black body. And so you don't have a huge amount of photons in the UV, but you have some. And those are not, that number of photons is what's going to ionize the neutral hydrogen. And so it will slowly eat out a strong Lorentz sphere of ionization around the star. Right? And so this, this sort of energy, you need this energy to remove the electron from a neutral hydrogen ion atom, and that's roughly, you need a photon of this wavelength or shorter to give it that energy. And this will photoionize this photon. So the number of ionizations is directly related to the number of photons that the star is producing. Although if you have really energetic photons, you can impart a lot of energy to the electron, which might then cause some collisional effects. And so there's some extra terms on there. So it's not purely one-to-one, but you can calculate it. So this will photoionize a volume around the star. We can ignore helium because helium's ionization potential is about a factor of 2 higher. And the cutoff is exponential. And so there's much fewer photons to ionize helium than there are to ionize hydrogen. Plus there's more, hydrogen is more numerous than helium typically. So generally we can neglect helium in most cases, but it does have an extra correctional term. So this cross section is relatively high. And so you have a photon passing around, and it's very likely that an atom will absorb it and ionize something. So we can estimate how far the typical UV photon travels in an H1 cloud if we have a density of 10 to the 3 atoms per cubic centimeter. And so this is just how far it goes, and we can estimate, this is just the number times, or the inverse of the number times the cross section. So right, this is related to, this is our alpha, 1 over alpha, and this is tau. So we want tau equals 1. So we move this over here, we calculate this, and roughly speaking, the photon can travel about 10 to the 14 centimeters, which of course is much less than 1 parsec. 10 to the 14 is close, not that different from a few AU. This light travels in about an hour. And so realistically speaking, the ionizing photons will only survive an hour in the cloud before being absorbed. So in this sort of scenario, we can develop a place where we have on the outside neutral hydrogen, on the inside ionized hydrogen, and then we have a boundary here, and this boundary is typically much less than this ionization radius, where this boundary might contain both H1 and H2. So this radius here is what's known as the Strong-Lin radius. And so after some time, once the system comes into equilibrium, there will be a radius at which you will have everything inside of this remains ionized, and the number of de-excitations or recombinations is equal to the number of ionizations. And so this sort of situation, you'll have a partially ionized region, then a fully sort of bound region. This situation, as I mentioned, this sphere is only of orders sort of 10 to the 14 centimeters thick. And this situation would be called an ionization bounded H2 region because it's bounded on all sides by this material. Actually, no, I got that wrong. So yeah, if you just let those photons go out, this should be ionization bounded. If it's surrounded by an H cloud, where this is basically if the H1 cloud is small enough for the star to be completely ionized, then we call it matter bounded. And the matter bound should be lower or smaller n than the ionization bound, right? Because basically what this means, matter bounded or density bounded, means that some of the photons escape. Okay, so in this sort of situation, we have electrons, protons recombine, and we can rewrite this recombination, the volumetric rate of recombination, as the density of electrons and protons time this recombination rate. Or this, this thing is the parameter specifying the recombination rate. So this this probability per volume per second. Okay, so what we want to do is match the number of photons coming out to the number of recombinations, right? And so one can sort of do that if this is just pure hydrogen, these are equal, and we set this up before to be 10 to the 3, and so we can ask what the volumetric recombination rate is, and we just calculate it. So we plug in these values, and it's something of a few times 10 to the minus 7 in these units. We can then estimate what the recombination time scale is, and that's just going to be the number density of electrons divided by this recombination rate. And so the 1 over the centimeter cubed here will divide out, and we just have a time. And so this occurs in about a few times 10 to the 9 seconds, which is about 100 years. And so typically you can set up a equilibrium state in a relatively rapid amount of time. So this is relatively short compared to the lifetime of an ionizing star, which might be of order millions of years. So over this period, we expect a steady state to develop relatively rapidly. And so we end up with this strong-Lin sphere of ionization. And so now we have a plasma. And of course, this plasma, you have protons, they have a Coulomb field, you have electrons. And so you have the potential to cool, where another vector for cooling besides recombination is via Bremsstrahlung or free emission. So we can calculate what the total number of ionizing photons are here as well. So if we assume that we need Lyman continuum photons with this wavelength, we want to know how many are emitted by the star per second. And so in equilibrium, the number here will equal this volumetric rate times the volume. And so we can plug that in, and we can end up with a derivation of the Strong-Lin sphere. And so plugging this in for typical values of, say, an O star, an O5 star, which has about this many ionizing photons. And if we have any, again, equal to 10 to the 3, we end up with a Strong-Lin sphere, which is about 1 parsec in size. And then the width of this edge, the thickness of the skin is much, much smaller than that, typically less than 1%. So we can ask what types of objects actually make strong wind spheres. And so one, of course, obviously massive stars, which is the example I just gave. Anything with a mass over about 10 or about 15 solar masses will be hot enough to have a surface temperature greater than 30,000 Kelvin. And that's hot enough to start generating UV photons, which can ionize the neighborhood. Typically, the stars are relatively short-lived. They have main sequence lifetimes of 10 to the 7, and then maybe 10 to the 6 lifetimes after that. So you'll see these generally in star-forming regions, right, because they have relatively low lifetimes. But that's a place where you might expect this. Another place to see this might be in old low mass stars. So stars between 1 and 8 solar masses. Once they've moved off of the main sequence, which might be 10 to the 10 years in total on the main sequence, they become red giants, and eventually then they will become white dwarfs. And the white dwarfs will be hot enough to ionize they will go through a planetary nebula phase, they will eject material, then they will condense down to become a white dwarf. The white dwarf can then ionize that material, right? And these are what's known as planetary nebulae. And mostly they're seen because there's a central source of ionization, which is just powering them and lighting them up. So, in this case, both of these cases, the ionizing source is roughly a black body spectrum with some surface temperature. And what we're looking at is the high energy or high frequency tail, where we want to count the number of photons above 13.6 eV. So this is just an example of the former NH2 region, and so you can see the fairly messy. Lots of this is actually fluorescing in this particular picture with the H beta line in red here, and then the UV photons are scattering and so forth. So there's other processes as well, but the one we're going to look at is bremsstrahlung. So we have collisions between the hot photoionized electrons and between the electrons and the ions. Everything is thermalized and become, on a relatively short scale, should come into local thermodynamic equilibrium. So we expect a Maxwellian distribution, check, and basically heating will be balanced by radiative cooling. And so we also will, it may be the case that in real situations we don't have just pure hydrogen, but we have metals as well. And so we'll have collisions with electrons with metal ions, and these can create sort of low-lying energy states, which can create line emission as well. And so some of the cooling will come from line emission, which we'll deal with at the end of the semester. But and in fact, the reason why people saw H2 regions and planetary nebula was because of the emission lines, typically actually oxygen 3, which is a forbidden line. And they used to call these things nebulium lines because they showed up in these diffuse nebula. So the Balmer recombination lines are at these two frequencies. They're the most common ones. They help the gas cool a lot. So these are the recombination lines I mentioned before. And so they're relatively strong compared to any continuum emission that you see. However, you can see continuum emission if you have sensitive enough instruments, and this continuum emission will be from bremsstrahlung. But the abundance of the ions here, is going to give rise to bremsstrahlung, and so we can see it. So what will this actually look like? So we have a couple examples of the spectra here. So these are the emission lines, but then there's this faint continuum as well, which we see. And this faint continuum, there'll be some scattered light from stars, but the bremsstrahlung emission will be in here somewhere. And typically you can use the emission lines to figure out what the strength of the ionizing source is. So whether it's from stars or from AGN. So this is a ionization diagram. So let's say we have a situation where we have the thermal equilibrium and between the heating and cooling. And so we have a temperature of about 10 to the 4 Kelvin. And of course, this is much higher than the typical interstellar gas. The gases are going to expand. This will reverse the infall of gravitational collapse onto an ionizing star. This sends shocks to the surrounding cold gas. And so you end up with a fairly sort of stable situation where you're inhibiting further growth of the star. You stimulate maybe the production of other stars in the region. And so these, the first stars that form will then ionize these regions and kind of start to cut off star formation. And so typical H2 regions have a size of about 1 parsec. They have electron densities of about 10 to the 3 to 10 to the 5 per cubic, basically electrons per cubic centimeter, and masses up to about 10,000 or so solar masses. And so they will produce free emission, which we will largely be able to measure in the radio band. And this allows us to estimate the electron temperature, the electron density, and the ionized volume, which is something we wouldn't necessarily be able. Well, there are some benefits of doing this. So what would the benefits of doing this be? I'll leave that for you guys to help me answer. So if we know these things, what can we get?
So maybe we could get the recombination rates or something like that.
Well, we know the recombination rates, right? Per cubic volume, but we can combine if this is in equilibrium, we can combine that with the source of the ionization, the UV photons. Mm. And in these systems, it's not necessarily trivial to measure or see all the stars, right? If I go back to this, right, where are the stars here? It's hard to see because they're extincted in the optical, and so we don't get a full census of all the stars. The benefit of the radio emission is that you can see all the way through because there's no extinction going on, and so you can make a full census of all the UV emitting stars in the region. And so you can measure the top of the IMF. You can measure what the spectrum of stars looks like individually, or white dwarf or whatever. So you can measure the temperatures of white dwarfs, for instance, where you wouldn't necessarily be able to. You'd be on the Rayleigh gene's tail in the optical, so you wouldn't necessarily know where it cut off, what its temperature was. So you can use this for a variety of things. So the benefit is that you can measure the ionization from these things. And so, then with an assumption about, say, the mass distribution for new stars, you can estimate the total star formation rate in each region, which again is not trivial from the opticals. So the radio IR data are actually a very useful way to correct or understand if you have a full census of what's going on in a star formation region. In planetary nebulae, as I mentioned, these are around white dwarfs. The white dwarfs have a temperature of up to 10 to the 5. So we're totally on the Rayleigh gene's tail. And the masses that they eject out, I mean, obviously the initial masses were of order this. So typically the planetary nebula masses are of the order of 0.1 to 1 solar mass in total. So they're much more compact, right? So you're only really seeing this planetary nebula mass over sort of the solar system, 10 to the 14, 10 to the 15 cm. But they end up, because they have a lot of UV photons, you can get interesting, they will have a different ionization structure than an H2 region. And they end up being relatively luminous indicators. So even though the white dwarf has a radius of only the radius of the Earth or so, it is because the temperature is, so that's, so a massive star might have a radius of 10 solar radii, and the Earth has, I guess the radius is about a factor of 300 less than the sun. So that's 3 orders of magnitude in different radii. And so when you square that for the surface area, that's a factor of 10 to the 6. But their temperatures are different by an order of magnitude. And the emissivity goes as temperature to the 4th power. And so even though they're 10 to the 6 fainter because of the volume, or the surface area, they're 10 to the 4 brighter because of the extra 10. And so in reality, they're not that, they're only a factor of 100 fainter than massive stars because of that. So they're still relatively bright. You can see them out relatively to relatively high distances. With one of the benefits of these guys, yeah? No, okay. One of the benefits here, yeah.
Yeah, I have a question. Sorry, I don't listen very well. I have a question in the previous slide when you mentioned that the free emission in radio band is useful to measure, well, to estimate the number of ionizing photons. I was wondering in this case, in which frequency would you need to know the spectrum? I mean, the integral spectrum in between which frequencies, or a specific band?
No, so you'll actually need it over several frequencies. Because if you only measure it on the Rayleigh-Jeans tail, then you don't know where the turnoff is. And what you really want to do is measure both, and then you measure the Rayleigh-Jeans tail. And that, where tau equals 1, if you can spatially resolve it, you can do lots of things with it, because tau equals 1 gives you the number density times the absorption coefficient, right? So you can estimate the number density of electrons there. And then the normalization of the total emission will be dependent on the number density squared and the temperature. And so you can then estimate various properties of the system.
Okay. Okay, thank you.
Okay, so the other benefit for planetary nebula is that they are a fossil record of the older star formation. And so if you can map them and understand them, they can provide you with a useful history of how our galaxy formed stars 10 billion years ago. Which is, of course, more problematic when trying to do that with massive stars, because they're very fleeting and they don't tell you much about the older star formation history. Okay, I'll sort of skip that. Here's just an example of a planetary nebula. This is, of course, an HT optical image with false colors, just to show you this is mostly line emission that we're seeing. This is the radio emission from H2 regions, or from planetary. These are all from planetary nebula. So you can see that this is actually a planetary nebula where you can see it in the optical from line emission, but you can also see it in the radio. Again, here very faint, but you can see here again. You can see it here. So these are actually, the radio is a wonderful way of finding planetary nebula throughout the solar system, or not throughout the galaxy. Sorry. So to sort of estimate this, it's relatively straightforward. So we have the emissivity, which goes as something like this. So it is related to temperature, related to the density, and has a frequency cutoff, which goes like this. And then we have the absorption, which goes like this. And so it has a much stronger frequency cutoff, and we can relate these two if they're at equilibrium like that. And this Gaunt factor for free looks like this. So in the Rayleigh-Jeans limit, this exponential here will turn out to be, actually this exponential turns out to be this. The -1s cancel, the minuses cancel, and you end up with just h nu divided by kt. The nu's cancel, and you have nu to the -2. Right? So so it goes something like nu to the -2. The Gaunt factor has a frequency dependence, and so it ends up looking something like this. It's very close, but not quite to. And so you can estimate the optical depth. And so the optical depth will look like this. So the line of sight, you integrate through it, and you use this factor here as a function of frequency. So you can plug in, roughly speaking, what these dependencies are. There's of course a constant here. This is proportional, but this thing, this tau ends up being proportional to this. So it goes as 1 over frequency. So at higher frequencies, tau is lower. And it's strongly dependent on the density squared, right, and the temperature. So at very low frequencies, we can then estimate what the flux will be. And the flux is going to look like you did this before with the Rayleigh-Jeans approximation. And so this flux here will basically be the Rayleigh-Jeans formula times tau. And tau is just this. So this flux, basically I screwed that up, but when tau is very, very large, this is optically thick. And so you end up having a very, very strong tau here. And the frequency should go as basically this flux goes as just as this factor here. At very high frequencies, when tau is very, very low, what happens is the two sort of cancel out, and you have this sort of should behavior. So this should roughly be flat with frequency. So there's this again is the small frequency from the Gaunt factor, but nothing else, right? So it comes in from the Gaunt factor alone, but not from here. Okay, so one can typically, estimate this as a cylinder. You have the tau going through it in the line of sight. This works decently. And so if you plot this flux, you'll have the Rayleigh-Jeans portion where it's optically thick, and you have a slope which is sort of around 2, or minus 2.1. And then you have a flat portion of it where the slope is just very minorly dependent on frequency. And this will end up being your, what you see. And then of course at high energies, higher frequencies, you will have the exponential cutoff, which tells you something about the overall temperature of the electrons. And ideally, you would want to measure all of that to really constrain the emission volume and the temperature and so forth. But often you don't have all of those, but you can kind of get away with estimating certain factors here. Okay, so just to sort of, I mentioned that these opacity coefficients here are proportional to this frequency. We can also measure the slope. Turns out the slope by radio astronomers is also given by alpha, so you have to be careful. This is the spectral index. And even worse, it's defined, depending on who you ask, as plus or minus. So you have to be careful about this. So basically, this is the definition is how fast this slope is changing, right? And so this is this index here of minus 0.01 or minus or 2.1, something like that. So in the low frequency spectral index, if we have a uniform H2 region, the slope should roughly go as plus 2. This alpha, where we have a negative sign here, so it should be nu to the minus alpha, right? So coming back to here, nu to the minus alpha, so alpha here would be 2.1. So this sort of convention is what radio astronomers use, but one has to be sort of careful about it. And so an alpha of +7 really means this. Yeah. So if you have an inhomogeneous H2 region, this will be, the slope will be about -0.1. and it's well above the break frequency. Or sorry, it will be about this well above the break frequency. And the break, what happens is, so this is for a homogeneous system where it's all uniform density. If you have pockets of different density, what's going to happen is that this is going to be different depending on exactly where you are, because this goes as density squared, right? Well, tau goes as the density times the cross section times the size. So it'll move around depending on the density pockets you have. And so you will get a blurring of this here in a more, I would say, realistic scenario, right? But you could also imagine a situation where you have a structure which has a density gradient. And so you could measure the density gradient by seeing where this turnover happened as a function of position. Okay. But the key thing is one of the other sort of aspects here is because the Bremsstrahlung is a strong function of density squared. If you have structure which has a strong variation in density, imagine a stellar wind. So a stellar wind that's constantly blowing will then have a radial profile which goes as r to the minus 2, because as you move out, these are the same number of atoms moving out, but the volume and the surface volume increases, right? The surface shells increase. And so you would have a density which goes as r to the minus 2. And so the free emission or the Bremsstrahlung from that would be strongly dominated by the material close to the star, and not so much by things far away from the star, because of the density squared effect. Just to keep that in sort of into your head. Okay, I've completely run out of time, and I still have many slides to go. So we'll pick this back up. Not so many slides, but 10 slides or so. So I'll pick this back up on Wednesday, finish this off, and then starting on cyclotron or gyro radiation. Okay. Any doubts, questions, thoughts? No. Okay. All right. Ciao, everyone.
Ciao.
Ciao.
Goodbye.